Hello friends, in this particular video class, we are going to discuss about unsymmetrical fault as a chapter that is module 4 according to VTU syllabus. So here, before going to start with the unsymmetrical fault, let us know the definition of unsymmetrical fault. That is nothing but here the unsymmetrical fault is defined as the faults in which the balanced state of network is disturbed are called unsymmetrical fault. That is the faults which the balanced state of the network is disturbed is called unsymmetrical, or you can say it as unbalanced fault. So there are two types in unsymmetrical faults. One is a shunt type of fault. So here shunt type fault is nothing but this type of faults involve short circuit between conductors or between the conductors and ground. So which involves short circuit between conductors or between the conductor and ground. Also they are characterized by an increase in current and increase in current. Here it is a mistake, it's not voltage. Increase in current and fall in voltage and frequency in faulted phase. So they are classified into three types. That is a single line to ground fault, that is LG fault, and LL we can say it as a line to line ground line to line fault. And the one is the last type is double LG. We can say it as double line to ground fault. You can see the representation. So this is a line to ground fault, the fault which occurs between one line and ground. Similarly, line to line ground, line to line fault, the fault which occurs between two lines, say it as Y and in between Y and B, or else in between R and Y, or else in between R and B. It is a line to line ground fault, that is nothing but double line to ground fault. The fault which occurs between two lines and one ground, either it is YB and ground, or else RY and ground, or else RB and ground. And the next is the second classification is the series faults. So here what in case of shunt faults that will be involved with short circuit between conductors or between conductors and ground. Here in case of series type of faults, here there is no short circuit, here open. That is here one or two lines in a three-phase system get opened while other lines remain constant or remains in contact, or else so that when one or two lines in a three-phase system get opened while other lines or line remains in contact, and this is characterized by an increase in voltage and frequency and fall in current in the faulted phase series type of faults, and this can be classified as one conductor open fault, two conductor open fault, and three conductors open fault. Here we'll be keeping one conductor open and other two conductors will be in contact. Similarly, in B, two conductors will be kept open by keeping one conductor in contact. Similarly, all the three conductors should be open. That we can say it as three conductors open fault. And the next is analysis of unsymmetrical fault using symmetrical components. So here consider a balanced three-phase synchronous generator, you can say it as alternator also, which is subjected to some unsymmetrical fault F at the terminal as shown in this diagram. That is, at the terminal A, the fault which occurs. The fault may be unsymmetrical one, but to the left of fault point F, the system is completely symmetrical. So that here consider a balanced three-phase synchronous generator which is subjected to unsymmetrical fault F at terminals. So here before the occurrence of fault the system is in symmetrical. Once the fault which occurs the system becomes unsymmetrical. Then the current of given sequence produces voltage drop of sequences only. Current of given sequence produce voltage drop of that sequence only, that we had already discussed in symmetrical components. Here the sequence impedances are uncoupled, they are generates positive sequence voltage only. That also we discussed in symmetrical faults. So here the following equations which follow, hence even during unsymmetrical fault also we'll get the equations here. VA1, that is for positive sequence voltage, negative sequence voltage, and zero sequence voltage, is given by EM minus IA1 into Z1, that we already discussed how we are getting. Since it generates the balanced voltages only, that will be positive sequence voltage for the generator, and rest of the thing here will be getting this VA1 equals to EM minus IA1 into Z1. For you can write here as VA, VB1, VB2, VB naught. We will be considering only one phase. So VA2 equals to minus IA2 into Z2. Similarly, VA naught is minus IA naught into Z naught. We can get from this network here. The VA1, by just applying KVL, we can get EA minus IA1 into Z1. Similarly, VA2 by applying KVL here, you can get minus IA2 into Z2. Minus indicates the current which flows in opposite direction. Similarly, VA naught is given by, that is a zero sequence voltage is given by minus IA naught into Z naught. So this we can write here. So this expression we already discussed here. The positive sequence voltage which generates here in case of generator, the sequence component of generator which generates only positive sequence voltages. So here we can write this in terms of matrix form, so that before that these equations can be called the system equations. For any fault at the terminals of a synchronous generator, the quantities that are to be determined are the three sequence currents, say it as IA1, IA2, IA0, and three sequence terminal voltages, say it as VA1, VA2, VA0, so that these are the expression we'll be getting. VA0 is given by EA minus IA1 into Z1. So these, whatever the expressions we are getting here, that will be writing in terms of matrix form. So that will be getting this expression. So for any fault at the terminals of the synchronous generator, the quantities to be determined are three phase currents of zero sequence, positive sequence, and negative sequence components.